Alright, yeah, I was gonna do, muons, and then just different optics. For if there's anyone listening, just different optics, night vision. There's like the white phosphor image, which is, this phosphor plate is technically an optic of the other night visions, and, so, you know, make the phosphor bigger. It seems like it'd become a bigger intensifier. I think you can just make it like a glass, and then you're just using electrons. You're using electricity to be able to, like a battery or something, to be able to have your night vision. I'll get into thermal, X-ray. But yeah, oh yeah, and then some evolution. But yeah. So technically, these linear accelerators and muons. I was just trying to like get sensitive to it, and so if they're saying that photons are technically if they're saying that photons are technically sorry, what is the word, decaying. So if photons are decaying, and within 5,000 feet they're turning into different forms of muons, if that's correct. I'm just saying, well, there should be like a dilemma there with the greenhouse effect. So I mean, I'm just assuming that there's all some form of dilemma with a greenhouse effect. I mean, I like when I'm like, if it's like kind of like a chilly day and I step out into the sun and I feel the sun, I don't feel like the actual photons are reflecting off of me. Okay, I'm on board with the photons actually traveling at a distance. Okay, it can be 8 minutes from the sun to the earth, and that's how long it takes a photon to actually reach me. Maybe it, but yeah, I'd still account for this oxidation. I'd still account for the oxidation cycle in the atmosphere. So whatever's happening in the atmosphere, there has to be some oxidizing process, and that oxidizing process has to obviously slow down the photons as well. Um, I mean, because we're talking about oxidation, or more particles, more bits being closer and closer to Earth. So the closer and closer you get to Earth, as in what they say is you enter the atmosphere. Okay. Um, this is also an argument for ozone depletion, and by O, they're talking about the oxidation zone, obviously, right? So by oxidation, well, I was going to say, first of all, when a photon enters the oxidation zone, which is technically what they're calling the atmosphere, even though they call it the atmosphere so they can say they have some greenhouse effect. I'm going to say that quite clearly, like the photosynthesis happens, or the photon synthesis happens as soon as it hits the Earth. I'm not saying that there can't be a reflection. I think that obviously there'd be some photoelectric effect. I think there'd be uh, photoelectric effect to the degree of seeing the blue sky, but I'm not really this proponent. I mean, I'm going to call it more of an illusion than like an actual greenhouse effect. So I'm going to say the blue sky is more of an illusion, but it's a very good illusion because, yeah, it has that distinction of the photoelectric effect, meaning that photons are basically terminating electrons, and by electrons I mean what is in the air, or the oxidation zone. So photons enter the oxidation zone and they eliminate, but essentially not eliminate, but yeah, you could say move around electrons uh, for us to be able to get like this blue sky. So I'm going to say it's more of an illusion. Okay, again, like just photons moving all the way, and moving like 100% into, like being absorbed 100% by the Earth or anything on the Earth. So if they're in the desert, or if they're in the savannas, then yeah, there's an absorption, and then there's an absorption with like darker clothes. So if you're wearing black clothes or white clothes, that's a difference in absorption. But I mean, you can only really feel that like if you're in really, savannah, Jesus Christ, like in a savannah or like a desert or something like that, I'd say. But you can still feel it if you're sensitive to the weather like that. Um, but I'm just saying, I would more so believe that there's a photoelectric effect happening, not a greenhouse effect, but a photoelectric effect happening that is causing this illusion um, of the blue sky, and that's just because there is a technical like uh, photonic reflection, but the reflection isn't. I mean, it doesn't make sense to say it that way. I guess you have to say that some of the photons are being absorbed and some of the photons are actually being reflected. More or less though, something more or less like a person. No, I don't think a person carries enough mass to be able to actually make a to make a full reflection. That's kind of what my point is. Um, so Yeah, I mean, again, of course, like there'll be like some reflection of the photons back in, like back up, okay, like back into the air, like it's gonna like hit the ground, and then enough of the photons will be absorbed, and enough of the photons will be reflected, and the ones that get reflected will have this greenhouse effect, but really they're just uh, you could say just decaying back into you could just say decaying back into the oxidation zone. Now, if in this photo multiplier experiment, it just seems like yes, there are actual photons that are actually decaying, and it's like sensing. I don't really. It's kind of obscure how they were able to sense these something like a muon. Um, Because if they could be saying that the ones that absorb the most, the photons that absorb the most, technically become muons, and the ones that completely decayed, I mean, that'd probably be the only logical way for me to look at it. The ones that completely decayed was just photonic decay, but the ones that actually made it to uh, the sensilator or whatever that thing is, or the sensor that was able to manage, so to speak, the photons, and they were just calling those photons muons or mesons. So, because obviously it's not going to sense something that doesn't get into its program or doesn't reach whatever it's programmed to learn. So, I mean, the AI or the photo multiplier, yeah, you could say. I mean, logically, to me, it would say that okay, there were some photons that were decaying, but it was a wave. Since it was a wave of quote unquote energy or quote unquote photonic energy or photons, then the photons that don't make it, okay, they're expressed as non-variables. So there was a bunch of variables, and the variables in the experiment that did make it, sort of like it was sort of like measuring like a heartbeat, like on one of those lifelines. So like on a lifeline, like it measures your heartbeat, and so every time it measures that pulse of energy, it measures it, and it's able to say that was their heartbeat. Like sort of in this one, it was upside down, so you could say that um, every time it measured energy, that energy was just uh, photons that actually made it and didn't decay. But it seemed like they were just calling them muons. So uh, that's kind of my early take on it. But yeah, I mean, it was pretty interesting. I mean, I have heard, so it's a linear accelerator, and I have heard that, not just a linear accelerator. Well, I mean, sorry, I have heard that the modern particle accelerator, the LHC, Large Hadron Collider. I have heard that they use a magnet, and maybe I'm wrong about this, but if it was like a reinforced magnet or like an electro, like well, obviously I don't even know if it'd have to be that, but I've just heard that when they form their collision in the LHC, the particle collider, that they have to have a magnet behind it, but that didn't really make sense to me. But I should probably look further into that. Um, but somehow that magnet is supposed to intensify what they see distributed, and then I thought they were just measuring photons, and then whatever variables that they had in the experiment would be a muon or a meson or cosmic soup and like a quark or whatever. So like if they ran the experiment and like they were running it, you just have all these collisions with the photons, all these reflections or diffractions, refractions, and everything in between. They were like quarks or something like that. So, but somehow they could only computer graphic image actual images if they could only use computerized images if they actually wanted to, or sorry, they could only use computerized images with magnets. But yeah, I'm not totally expert on that. So, because yeah, it doesn't really make much. Well, the whole experiment just in general doesn't make much sense to me. But linear accelerators definitely cleared that up a little bit. So yeah, I was trying to get into different optics, and it seemed like it seems kind of obvious, but yeah, I guess you can have like if you have like regular vision through binoculars. Say there is like a little bit of expansion. These binoculars don't really seem to have mirrors. They just seem to have like reflection. They just seem to have actual the lenses, like the curvature of the lens is what gives you a certain image. It was also interesting with the eye and understanding how the eye sees at wider image, like fish see uh, monocular images, and I think humans see binocular, meaning humans use both of their eyes at the same time, and fish use one frame of vision at the same time. But it also seems like fish can see in front of them, but they do like fish having eyes on the side of their head. They do seem to have a blind spot, which I think is pretty interesting. But then you have like seals and I think whales. Well, no, whales technically would have monocular vision on the side of their head too, but so yeah, like you have something like phosphor, like this phosphorus. I mean, it just seems like a piece of glass, and it could intensify the image, and it would intensify the image by um giving you like a white vision. So it's called like white phosphorus image intensifier, and it seems like you can just get a more detailed picture through any scope, any lens, and sorry, with this white phosphorus, and it'll give you like a better scope. I want to say that they put it at the beginning of the lens, so as soon as you look into the lens, you would see um, like the phosphorus image, and they also it just seems like there's just wires and sorry, like there'd be like some battery that is for like night vision, and the battery is somehow able to uh, speed up the image. So it's almost like there's a I don't want to say like there's a flash, but if obviously like you're using night vision, like you don't want to go outside because there'll be like a lot of photons or like a lot of electrons that they'll use, and you'll multiply the amount of electrons you'll use when it goes into the focus. So that means like it's going to be like really bright. So that's why you get like a really bright image if you use night vision during the day. But if it's at nighttime, then you're not multiplying that many electrons and photons, and they just get particleized. That's not a good word, but yeah, they get like the particles get multiplied, so it seems like there is like some flashing images. I mean, it makes you think of like recording devices. Like a recording device, it just seems like it's technically it's just like a camera with film, but it's repeatedly taking film. Um, it's just repeatedly taking film, but then somehow it gets like imprinted on a memory chip, like a memory card. I mean, that stuff is insanely cool. I mean, it just seems like it all sort of came about with like LED, um, and like the internet and things like that, and like computers in the 80s. I mean, not just necessarily the internet, but yeah, like as soon as they figured out the camera, that they were somehow able to like uh expand the film. But then once they electronic like they yeah, they made the film electronic, then that means that the electronic would have to be somehow imprinting images on like some sort of memory card, which is like really interesting. I'm not gonna lie, it's really interesting how they do that. um and then like you could say, so that's like night vision. Night vision is kind of just like night vision is kind of just it's taking in photons at night, okay, and then it's somehow multiplying those photons. It's taking in whatever photons or electrons it can see at night, and then somehow it's multiplying those images, and then so you see through the focus, and you can use like phosphorus to kind of get like a higher definition of like just this glass that'll give you like a white image instead of like a green night vision image. It'll be like a white vision, or it'll be a white image, and it just seems more high definition, and that's just like a piece of glass by your focal point. But yeah, whatever is happening in there, it just I would say, like it's electricity. So what you're seeing technically, like if you turned off the night vision binoculars, technically you just see like a dark image. But when you turn on the image, that means there is energy. So the energy is somehow reproducing, like maybe at extreme electronic speeds, magnificent speeds, and that's how you're able to produce like an actual image. Because yeah, it doesn't really seem to have anything to do with thermal, but how disassociated are these things really? Because if you have thermal, then like technically, I mean, I would say that they just have to be because it's supposed to be sensing, so they have sensors, and sensors always have to do with like um thermal, but they can also be with like radical electrons or high like a high radiance of electrons, and those electrons could be firing and seeking images, and seeking out images. Like, I mean, let me try to finish this thought. So seeking out images, whatever's hot, like if it sees a person, then it'll be able to fire more images at it. Because I mean, it's not going to have thermometer. I mean, it doesn't seem like it have thermometers on it. It doesn't know what's hot or cold. It's just firing an exuberant amount of photons. So if there's photons being absorbed, then you could say those photons would somewhat reflect. They wouldn't just completely get absorbed like a piece of wood would just completely absorb photons. But like if it was like a hot, warm body or an animal or something, then it seems like those photons would have a different measure of absorption, or either that they would have a complete absorption, and but I still think that would entail some some reflection. But to go back to the other topic of muons, but yeah, so it's pretty interesting. And then of course I lost my train of thoughts. Yeah, and then of course I lost my train of thought with whatever else I was trying to talk about. Um, but yeah, I mean, and then the X-ray. Okay, that so the X-ray is technically, I mean, it's going to be like, to me, X-ray. Correct me if I'm wrong, but it just seems like an exuberant amount of, um, like you don't even have enough electricity to be able to bargain with for binoculars. Like you have to have an actual X-ray machine. Like you're not really. I don't think a pair of binoculars could actually fit like a battery that the size that could create one of these linear accelerators, or create one of create like an actual X-ray. So the actual X-ray is, I would say, that powerful because it seems to be even well, it's even more radical than it's even more radical than UV rays, right? So it could just so you're just amplifying what was it like amperage and we're talking about amperage and volts or amperage and watts, like lower watts. Um, is basically how fast they're going to be distributed, and amperage would be like the actual intensity. So yeah, you're just talking about like if you're just increasing the amperage, like the Ampere's law or whatever, like how much electrons you're actually enforcing, and so into the world, I guess, and so yeah, you're increasing the amperage from like you know infrared to UV and then to X-ray. And so it just seems like X-rays are extremely amplified, and that amplified is so strong. Um, in my opinion, that it'd be able to sense it just goes right through your skin, and it's able to sense like your bones. Okay, so it's able to go right through your skin. It's able to sense your bones. Um, or like they do brain imaging. Okay, brain imaging might be like brain imaging what is it called? uh I don't know, brain something imaging, but no, I don't think that's what it's called. But whatever. But so like they might try to do some images on your brain or your body, and like it's just X-ray, so it's going to be like a excruciating high rate of like that's why I think they're just taking pictures too. They're just taking single pictures. They're not firing X-rays at you, so they can do this to your brain and get like a MRI. That's what it's called, and they can just get these they can just get these photographs. But as like essentially, these are very radical. This is like a very radical amount of electrons. Okay, so like cause damage and all that stuff. Uh, and I think then after that, there's gamma rays, and I'm not too sure. Gamma rays just seem more of like the most potently radioactive. Um, and yeah, gamma rays. I don't know. I'm a little bit confused by gamma rays as well because it just seems like, well, are they, like are they? I mean, because it's not radio. I mean, radio waves in this uh, consensus is like radio waves are the least harmful, and then thermal, and then UV gets stronger, and then X-ray gets stronger, and then you have gamma rays are the strongest. So I don't know. Um, I mean, gamma rays. I guess we're just talking about extreme radiation, but I mean, I don't want to say they're associated with like nuclear radiation, but maybe they are. I mean, that sounds about right, but I can't really explain how nuclear radiation, just a little bit of nuclear, or I guess a lot of nuclear radiation compared to like X-ray. I don't know. Um, yeah, I don't know. Gamma rays seem pretty tough, but anyway. All right, so just to be formal, just to be formal, I don't really think that these geological well, whatever. I don't really even know what to call them. Like these isotopic experiments. I mean, these are all basically derived like from maybe 60 years ago. Um, I think in terms of the the life of Earth, or so just actually having more substantial evidence than just saying the Earth is really old. Like they actually had the machinery, the technology to be able to measure the isotopic um, decay and things like that. So it just all seems really extreme, and I mean they're like either 50 million years off or uh, 50 million years too soon or something, and then it goes all the way back 4 billion years. So, but yeah, I mean, I guess you can say somewhat that there is isotopic evidence for, I mean, clearly that it like the Earth is this old, but I mean, much more substantially, much more, especially much more, I should say, than their Big Bang theory. Because I'm just not really too, I'm just not really too, yeah. I mean, it's up, down, left, right, forward, back. You have those extremes, and how are you going to deal with that? And then also dealing with like the whole living force, conscious universe thing, and like the universe knows what it's doing, or especially the Fermi paradox and the Fermi paradox just being, I know Fermi did more things in physics, but just the Fermi paradox, uh, in that they think that there is other evolution going on out there, or if not evolution, then what are the limits of evolution, or how could evolution progress differently? Like, I mean, so that is where I kind of get carried away. That's what I really don't much like. Just because they are guesses, they don't have any evidence at all, and I mean they have actual clear evidence for isotopes, degeneration or decaying and things like that. But I'm just saying, in terms of the bigger picture, how are they qualifying that we're going to evolve into anything else, or that like fossil fuels aren't a finite resource or things like this. So it like the idea is that they have this the they have precellular unicellular or single cell organisms, and then multicellular organisms. And so precellular, they don't have any real evidence at all, I think is what they said. So they can't even test anything that is precellular in a lab. They're just saying, well, there was an oxidation process, and they call it the oxidation event. So there must have been, and they also use the term biological oxidation. So there was biological oxidation happening without any biological life. But I mean, you can understand that there must have just been unicellular or multicellular, but all they can really test, I want to say, because unicellular life is what exists uh, in it exists in multicellular life. So a multicellular organism, technically has to use other unicellular life, like the mitochondria. And so the mitochondria is what helps process, correct me if I'm wrong, but the multicellular organisms. So the multicellular organisms are able to grow, but they also need unicellular, that's a hard word to say, action on their behalf to be able to grow. So they can't create anything that is unicellular, from my understanding, because they just go right to multicellular, and then they continue to grow multicellular organisms to actually see if there's any evolution in these multicellular organisms, and they try to speed it up, or they just try to grow insane amounts. Like they're talking about yeast, and supposedly this yeast, even though it has, technically it should have mitochondria. I might be wrong. I think it's multicellular. Um, but yeah. So it's dealing, and then again it deals with like these eukaryotes and prokaryotes. So uh, I am like pretty confused about all this stuff. I mean, I should get into it more, but um, I don't know if eukaryotes are pre-cellular and prokaryotes are unicellular or something like that. But yeah. So, and I know they have like fossils and all that stuff, but in terms of what they're like, in terms of what they seem to be implying was that they can only use, like, we only have evidence of multicellular life. Multicellular life needs unicellular life, and they can't do anything with unicellular life on its own. But they know that before cellular life, there had to be some single-celled organisms or unicellular cellular life, which they can't derive from any realistic experiment. So again, like they're just growing multicellular organisms, like certain algae and stuff like that. But they seem to be prokaryotes because I think eukaryotes maybe came before, like before the cells were able to develop or something like that. But it all basically revolves around this oxidation process, and the oxidation process is what was able to give um, the oxidation event, which is essentially what happened. Like you hear 2 billion years ago, the oxidation event happened. So 4 billion years and then 2 billion years later of Earth, oxidation happens, and then it took about 500 million years for any cellular action to like prosper, for like any for anything to really go, like anything to really happen. I guess become multicellular because yeah, like a single celled organism can't survive on its own. I think that might be a eukaryote, and then a prokaryote is a multicellular organism, but I'm probably wrong again. Again, for the however many times I've said that, because it just seems like yeah, the unicell is the mitochondria, and the mitochondria is what is able, like it needs mitochondria, so it needs more than one mitochondria to be able to survive or something like that. But basically, it's this oxidation event, and so it just seems like there's a lot more decay and reflection going on, essentially, more than like any sort of greenhouse effect. But we do have this oxidation zone. So they can say that gradually our oxidation zone is depleting because of, well, yeah, because of, I mean, we're, we're using carbon fossil fuels, and that's releasing methane, I want to say, and the methane is what is degrading our oxidation zone, and our oxidation zone is also being depleted essentially because we're cutting out a lot of photosynthesis. So there's not a lot of photosynthesis happening. More radiation due to the methane releases. And yeah, so that's why they're saying that we're going through a warming process. Okay, so that's technically the like sixth mass extinction is this warming process, and the warming process is um going to, yeah, it's like warming, gradual warming of the earth, and also like depletion of oxygen in the waters. So not only just photosynthesis, but water oxidation. Like I used to hear a lot about that, but who knows? Like by 2040, I mean, because if all, like supposedly if all of the coral reef is taken out, supposedly like I don't know, all like are they saying like all the plant matter in the whole ocean is dead, and then if like the coral reef is like the ocean's last chance, and if they take out, or maybe the coral reef is just so substantial to oxidation in the water that if all the coral reef dies, then if all the coral reef dies, then there'll be no oxygen in the waters, and then uh, sea life won't survive, but especially there won't be any oxygen in the water, so that'll just completely, uh, deplete our it'll be more of a depletion to our oxidation zone, like our oxidation zone. Also, like, yeah, it just seems, the oxidation zone is a much better word than uh, this greenhouse effect happening because, yeah, it doesn't really seem too substantial. Um, and yeah, I mean that has a lot to do with overpopulation and things like that. So uh, not really, not really anything surprising, I guess. But yeah, and then so these muons, I would just say that they were it's just turned into cosmic soup. It's just turned into like these quarks and whatnot, and they're the you could just say the photons that did get through in the photo multiplier or the linear accelerators. The photons that do get through, they show um, as muons, when really they're just photons that didn't decay, or photons that were able to get absorbed, or photons that were able to reflect. I wouldn't put too much. I mean, because the thicker, and the idea would be is that like the less was it like the less sorry the less oxidation you have, you'd say there's more radiation because more photons are radiating. There's more photons being absorbed. There's more photons being reflected, and therefore you have a higher radiation from the sun. So the thinner the oxidation zone, again, more photonic energy reflecting or absorbed, and so that's what you're really looking at. You're not really looking at like this greenhouse effect where the photons are bouncing all around. They're um, bouncing off of the Earth and all that stuff, and causing this greenhouse gas effect. I mean, you're really looking at just photons in or out of the oxidation zone, and then the depletion of photosynthesis and all that would cause photosynthesis or oxidation in the waters or on land. That's that's gonna there's gonna be less oxygen in the air, so there can be more radiation from the photons. So yeah, I just said that like twice. But anyway, yeah, and then you have like night vision and all these things. They're just using electronics to emit or yeah, essentially emit more energy. But it just seems like they have, it's this film thing, and how are they, um, even though it's not so much a photo multiplier now, and it's just a pure recording device. Is that recording device essentially? It's running off of a battery, like a lithium battery or something, and that battery is able to charge the photons enough for it to be imprinted on some. But I mean, technically, if you're not recording something, then the images are just flying by um, at a certain rate. So, like, you're seeing through a lens, but is that lens? How is that uh, lens? I mean, essentially, again, with binoculars, you're not recording anything. You don't really need to record it onto anything. So there's nothing going into a like a memory card or anything. There's nothing like that. It's just you're seeing the image that you're seeing. So but yeah, that's a pretty interesting subject. And then I was just assuming that with thermal energy, you're just firing a bunch of photons out, and the photons is going to absorb into whatever actually has heat, like whatever is actually hot, like whether it's the light socket or, well, yeah, I guess the light socket or a human body or an animal. Um, it's going to the photons are going to fire more rapidly or be absorbed by that image in your thermal. So that's what I think about thermal vision, because it's kind of like X-ray in that you're just sending a huge amount of force, a huge amount of electrons at because then this is again just a photograph. So you're sending a huge amount of electrons and a huge amount of force um, at like a person's body, for example, and it's not going to be able to fire through. It'll be able to fire through the force of the electrons will fire through the skin and all that, but it'll hit the bones. Or you could do that with a brain scan, and like brain scans, there it just seems like yeah, they're doing the same sort of thing, like radiating the brain so much, and they're firing the electrons, and they're just able to see the images because they're able to see clearly um, the movement and all that stuff of the brain waves, or like the energy of the brain waves. So, and then yeah, and then all the Yeah, so that's linear accelerators, and then yeah, the pre-single and multicellular life. Um, that all seems, 2 billion years ago during the oxidation event. You can't have DNA without mitochondria, and the mitochondria seems to be a unicellular life form. But also a unicellular life form, mitochondria, can't exist without other cells. Therefore, they can't really test it. It's not really testable. So they only have multicellular life like bacteria, and that bacteria they just grow that. And I think uh, eukaryotes are like a predisposition to cellular life, and prokaryotes are cellular life. But I'm not too sure about that. Yeah. So